This model, this is wind power generation. Wind power generation rating is around 3000 watts. And then here we need to maintain the voltage around 400 volt. And then input voltage, here the detail. That means we need to design the boost converter because the wind turbine is connected to the PMFG. The PMFG will be converted into AC to DC by using this diode rectifier. And then this rectifier output will be boosted to 400 watt by means of this boost converter. So we need to design this value of LNC. So in order to design LNC value, here we are using this formula. The rating of the wind turbine model, the wind generation model 3000. The input voltage at a rectifier side is around 250 volt. And then here we are consider 5 kilohertz for the pendulum generator. And then output voltage we are consider as 400. This is the equation used for calculating LNC. So this is I out max at the converter voltage, which is converter output end. These are the percentage of the ripple inductor current and the capacitor voltage. So this is the formula for LNC. So this is the standard formula for calculating LNC for boost converter. While executing this one, we will see the results. This is the LNC value for this boost converter. And here we are using 2000 watts PV panel. Here the voltage is around the input voltage is around 250 or 245 point something. And then the output end we need 400 volt. Based upon this power rating and the output voltage, we need to design this LNC value. This is also now boost converter here we are using. For design, we are using this equation that means based upon solar PV power input voltage of the solar, that means the terminal voltage and then switching frequency and then output voltage requirements. Here we are designing the value of LNC. This is the value of LNC for that PV boost converter. This one. And here we are using load here we are using 3000 watts load, and here we are using battery rating is 2012 watt, but means the battery terminal voltage is around 240 volt, and then output will be 400 we are fixing. This bidirectional converter will be act as a boost converter concept only, but the current direction will be vary according with the power and the wind and the PV and then load. Here we are going to design the bidirectional converter LNCVD based upon this value. We are taking the power of the PV and then input voltage is nothing but 20 into 12. The output voltage is 400. At switching frequency is 10 kilohertz. The remaining equations are same for boost converter. Just I'm going to only response LNC value for that bidirectional converter. With the designing here, we are using P&O MPPT for controlling this boost converter, wind side boost converter. For it, we are going to measure the rectifier voltage and the current. To measure rectifier voltage and current, when we process via P&O MPPT. Here we need to fix the different parameters: initial duty cycle and maximum duty cycle and minimum duty cycle, and then change in duty cycle. And then here we are going to fix V volt, P volt, T volt. That is to indicate the previous instant voltage, power and the duty cycle. Initially, you have to provide some value for the previous instant values V volt, P volt, and T volt. V volt equal to 0, P volt equal to 0, and the D volt point be taken as the initial duty cycle. And then here we are calculating power, and then here we are calculating change in voltage, change in power, and then here we are checking the change in power. If change in power less than 0, here we have to check the change in voltage. If change in voltage is less than 0, you have to decrement the duty cycle, or else you have to increment the duty cycle to get the maximum power from the PV plant. And if this change in power is not less than 0, again we have to check a change in voltage. If change in voltage is less than 0, then you have to increment the duty cycle or else decrement the duty cycle. Based upon this condition, you have to calculate the duty cycle. After calculating the duty cycle, here you have to check the duty cycle value whether it is in between D max and D minimum. If suppose it's not in between D max D minimum, just you have to maintain the duty cycle with the previous instant duty cycle. After doing this one, next you have to overwrite the current instant value with the previous instant value. That's why we are doing this calculation. D volt equal to D, V volt equal to V, and P volt equal to P. This will be keep on exhibiting to extract the maximum power from the P. So next, this boost converter will be controlled by its of the NC algorithm. So here we are measuring the PV voltage and current. So based upon PV voltage current, we have to change the duty cycle. Here this is the equation for that algorithm for that incremental conductance MPPT. So here also we need to fix the different value, that means initial duty cycle, maximum duty cycle, minimum duty cycle, and then small change in duty cycle. And here we have to fix the initial value, that means we have to fix the previous instant parameter V volt, P, I volt. and then you have to fix the value for a previous system values initially. P volt equal to 0, P volt equal to 0, I volt equal to 0, and D volt equal to D initial. And then here you need to calculate power, change in voltage, change in power, change in current. First you have to check here that we need to check dV, that means change in voltage is equal to 0 or not. If it is equal to 0, then you have to check the change in current whether it is equal to 0 or not. If both are 0, then you have to maintain the duty cycle with the previous instant and duty cycle. If suppose this dA is not equal to 0, then you have to check dA is greater than 0 or not. If dA is greater than 0, you have to decrement the duty cycle, or else you have to increment the duty cycle to extract the maximum power from the PV panel. If suppose the dV is not equal to 0, then you have to check this condition dA by dV, which is equal to minus I by V. If this condition true, then we have to maintain duty cycle which is previous instant duty cycle. That means the already PV panel is operated to maximum power point. If suppose this condition the dAVDV is greater than minus IVB, then we have to decrement the cycle or increment the duty cycle in order to make the PV panel voltage or power, and then we have to change the PV panel voltage in order to get the maximum power from the PV panel. After doing this one, you have to check the value of duty cycle whether it is between D max and D minimum. If it is within D max, D minimum, no problem. You have to use that duty cycle from that incremental conductance MPPT. Otherwise, you have to equate that duty cycle which is equal to old duty cycle. Here you have to replace the previous instant duty cycle voltage, power and current with the current duty cycle voltage, power and current. Keep on executing in order to get the maximum power from the PV panel. Next thing here we need to control this bidirectional converter. Here we are going to apply voltage control method. That means the DC bus voltage going to be maintained at 400 volt. Further we are measuring the DC bus voltage, and then it's going to be compared with 400. It's going to be processed a PA controller. The PA controller will be generate the duty cycle. So the duty cycle is going to be processed by a PWM generator, and it's going to be generate the pulse. This pulse is going to be controlled this through IGBT in order to maintain 400 volt across this DC bus. The output of this duty cycle process by PWM generator and going to be control this IGBT. The output of this INC duty cycle is processed by PWM generator, and it's going to be control this IGBT in order to get the maximum power from the PV. This will be control this boost converter to extract maximum from the PV. Now I am simulating the model. Here I change the irradiation from 1000 to 500 and then 10 watts per meter square. So initially for 1000 watts per meter square, the power is around PV for around 2000 watts. For 500 watts per meter square, the PV power is around 1000 watts. For 10 watts per meter square, power is around 0. Because of that, you can see that the battery charging discharging will be vary. So from 0 to 0.6 seconds battery in charging condition. After 0.6 PV power goes to 0. That's why battery comes to discharging mode, because there is no power in the PV. For that condition, the battery comes to discharging, because here we are using around 3000 watts power DC load. And also here you can see that power generation from the, so this is power generation of the wind generator rectifier power. It will generate around 2000. Here during that time from 0.6 to 0.9 second battery comes to discharging mode. It will generate only 2700. Here we are having DC load around 3000 watts. In order to supply the remaining power, the battery goes to discharging mode. Here you can see that initially battery goes to discharging and comes to charging mode, and then it again comes to discharging and then comes to charging mode. This nature going to be very depends upon PV power and wind power. Here you can see that this is a PV power, wind power, battery power, load power. This is a power. That means say here the power going to be managed according with the PV power, wind power and load power, and also battery will be goes charging and discharging mode according with the variation of the source power, like that means source power, PV and wind power. And here you can see that the DC load power is maintained constant and the DC bus voltage maintained around 400 load. This is DC load current. Here the power going to be managed according with the power generation in the PV and wind. During that time battery comes to that means battery goes to discharging mode when there is power shortage in the PV and wind. Battery going to be manage the power to the load. That means battery going to supply the power to the load according to PV generation and wind generation. This is the working of this model. Thank you.